couldn't ever be my sunrise, sunrise, sunrise. You're just a setting sun, I'd pray and you would pass me by. You're only...
In this video, I want to give several examples of the first isomorphism theorem for rings and quotient rings. And this is going to very closely follow the presentation on page 243 of Dummit and Foote. So first, anytime we have an ideal of a ring R, we can take R mod I and ask, what is it? And apply the first isomorphism theorem for rings. So what are some ideals that we know we always have? Well, just like in the case of groups, where you can ask, what are some subgroups you know you always have? R is an ideal of itself. It's easy to check that it satisfies all the things you need in order to be an ideal of R. And R mod R is isomorphic to just the single element 0, so the trivial 0 ring. If you take just the additive identity, that's an ideal of R as well. And R mod this trivial ideal is isomorphic to R itself. This is just like a group is a subgroup of itself, and the identity gives the trivial subgroup of a group. Okay, so an ideal that is not all of R is called a proper ideal, and an ideal that is not just the additive identity is called a non-trivial ideal. So one of the interesting ideals is everything in the middle, the proper non-trivial ideals. All right, let's look at another example. Let's take nz, a subset of z, where n is some integer. It could be 0, and then you would get the trivial ideal, but it could be anything else. This is an additive subgroup. It's also easy to check that it's closed under multiplication, but even more is true, that if R is any integer and x is in nz, that means x is n times something. That means R times x is R times n times something. So in particular, it lands in nz. So this is an ideal because it's closed under multiplication by elements of the whole ring, not just closed under multiplication by elements of the ideal of nz. Okay, we can say something better here, which is these are all of the ideals of z. And how do we know that? Well, for one thing, ideals are subgroups. And we know that every subgroup of z is the trivial subgroup or is nz for some non-zero integer n. So because these are all the subgroups, it's definitely all the ideals. All right, so let's say that I is nz, just for notational convenience. So what is z mod I? Z mod I is z mod nz, this usual ring of residue classes modulo n. So we have this ring z, this ideal nz, and the quotient is the z mod nz that we have come to know and love. All right, so the next example I want to talk about comes from polynomials. Let's take z bracket x, so polynomials in one variable, coefficients in z. And let's take I to be the set of all polynomials whose non-zero terms have degree at least 2. So what does such a thing look like? A to the n, x to the n, a n x to the n plus a n minus 1, x to the n minus 1, plus a3 x cubed plus a2 x squared. What's the difference between this and an arbitrary element of the ring? Is that the linear and constant terms of this polynomial must be 0. Okay, I is an ideal. This is easy to check. It's an additive subgroup. You add two things in this form, and the coefficients just add. You're not going to pick up a non-zero term of degree 0 or 1. And if you take a polynomial in this ideal, something that looks like this, and you multiply by any polynomial in z bracket x, you're going to get one, all of whose terms have degree at least 2. Why? Because how do you multiply polynomials? You just multiply all the terms together, and then you combine the terms that have the same degree. So what happens when you multiply terms is you add the corresponding exponents. So if all of these have degree at least 2, and all of the ones in here have degree at least 0, you're going to get a bunch of stuff that has degree at least 2. All right, so here's a ring, here's an ideal. What is the quotient ring? So I'm going to pause and erase, and then we'll talk about this quotient. Let's continue our discussion of this example. We have z bracket x modulo this ideal given by polynomials whose terms all have degree at least 2. So what do the cosets of R mod I look like? Well, when are two polynomials p of x and q of x in the same left coset of I? That is when p of x is equal to q of x plus something in I. So p of x is q of x plus something with all terms having degree at least 2. So what does that mean? If the p of x and q of x have different x squared terms, you can just add something which has all of its terms having degree 2, and you can match up the x squared terms. But there's nothing you can do to match up different constant or linear terms. So two polynomials are in the same coset if and only if they have the same constant term and linear term. So what do these cosets look like? What do elements of this ring look like? Each one corresponds to an a plus bx, where a and b are integers, some chosen integers. So just to give a really concrete example, 3x cubed plus 7x plus 1 and negative x cubed plus 2x squared plus 7x plus 1, these are in the same coset because this polynomial is equal to this polynomial plus something, all of whose terms have degree at least 2. Okay? I mean, we have seen that this is an ideal, so we know that R mod I is a ring. But to be really concrete about it, what do the operations in this ring look like? If you have a coset of I, it's determined by some a plus bx. Let's say the left coset of I containing 1 plus 2x. And let's add it to some other coset, the coset containing 3 plus 4x. Well, you just add the corresponding linear and constant terms, and that is the left coset of I containing 4 plus 6x. That's easy to check. Same thing, how does multiplication work? You just multiply the corresponding linear polynomials. And when you multiply linear polynomials, you'll get some kind of x squared term. But it doesn't matter what the x squared term is, because you can always add some element of I to get rid of it or change it. So if we take 1 plus 2x plus I times 3 plus 4x plus I, what we get is 3 plus 10x plus 8x squared, but 8x squared is in I. So this is the same as 3 plus 10x plus I. Okay, so what's the point of focusing on an example like this? Well, it has a property that you might think is a little surprising at first. This ring R, z bracket x, does not have any zero divisors. But R mod I does. If you take x plus I times x plus I, what you get is the left coset of I containing x squared. But that is the left coset of I containing 0. That is I itself, because x squared is in I. So the important thing that leads to this example is that I contains this polynomial x squared, but it doesn't contain this polynomial x. So there are things that you can multiply and land in I, none of which are actually in I itself. So this is an example of something that's like a classic algebra exam type question. You should be aware that it's possible for a ring R to have no zero divisors, but a quotient ring R mod I to have zero divisors. Let's next talk about a really different kind of example. Let's let A be a ring, X a non-empty set, and R be the ring of all functions from X to A. So this is something that we saw very early on in our first discussion about rings. This is so general that it's very, very different than starting with something like z bracket x. So let's take an element C in X. We can define this map given by evaluation at C. And this is a ring homomorphism. So let's say EC goes from R to A. It takes a function from X to A and sends it to its evaluation at this particular point of X, C. So it's defined by EC of F is F of C. What is the kernel? Well, it's all the things in R, all of the functions where f of c is 0. So A is just some ring, so it's whatever the additive identity of A is. This map is surjective. If you take any A in the set, any A in the ring, you need to find a function from x to A so that when you evaluate at C, you get this little a. And you can always just take the constant function, which sends anything in x to A. And there you evaluate at C and you get A. So you can check that this really is a homomorphism of rings. I'll leave the details to you. But the quotient then by the first isomorphism theorem is that R mod the kernel is isomorphic to the image. So R mod the kernel is isomorphic to the ring A. So for particular choices of A and X, this might give you something interesting to think about. So I'm going to pause and erase, and we'll do one final example. Let's discuss the last example of this lecture. Let's take the ring homomorphism given by phi, which goes from R bracket x to R, defined by taking a polynomial and evaluating it at 0. How do we know this is a ring homomorphism? Well, we checked this in the last lecture in the case that R was given by the rational numbers, and the argument goes exactly the same way in general. So I'll leave that as an exercise for you to check. What is the kernel of this homomorphism? It's all the polynomials in R bracket x with constant terms 0. Those are exactly the ones where you evaluate at the additive identity and you get 0. What do the cosets look like? When are p of x and q of x in the same coset of kernel of phi? Well, that's exactly when p of x and q of x have the same constant term. So what do elements of R bracket x mod the kernel look like? They are determined by possible constant terms, by elements A and R. So what we get from the first isomorphism theorem is this map here is surjective because the constant term can be anything. So R bracket x mod this kernel is isomorphic to R. So our last example is really just following up on this previous one, where you can start with one ring homomorphism, and just like you can compose homomorphisms of groups, you can compose homomorphisms of rings. So we start with phi, we can compose with any homomorphism that goes from R to S and get a homomorphism psi following phi, which starts at R bracket x, sends things to R, then sends things from R on to S. Okay, so you can check that you really believe that this is true. So if you take the particular example where R is equal to Z and S is equal to Z mod 2Z, now we just have to describe like what is the homomorphism that we're choosing from Z to Z mod 2Z. And we talked about one in the previous lecture, this standard reduction modulo 2 homomorphism, where you send even numbers to 0 and odd numbers to 1. So what is the kernel of this composition, this ring homomorphism given by composing these two? Well, the things that psi sends to 0 are the even integers. And the things that phi sends to even integers are polynomials whose constant terms are even integers. So the kernel is all polynomials with even constant terms. Okay, so maybe this is not obviously true, but because this set of polynomials is the kernel of a ring homomorphism, it's an ideal. So you can also check directly that this set of polynomials satisfies the properties that you need for it to be an ideal. Now, what does the first isomorphism theorem tell us? Well, this last function is surjective. This function is also surjective. So the composition is surjective. So R bracket x mod this kernel is isomorphic to S, which is Z mod 2Z.